All right, let's take a look at this homework from 1.5. All right, question 1. If f is continuous on the entire real number line, negative infinity to infinity, what can we say about its graph? All right, well, first thing is that because we have not what I wanted. Clear that out. The things that we cannot have whenever we have a continuous graph is a hole. Okay, you can't have a hole. We want to be able to draw this thing without picking up our pencil. So a hole would look like this. We have a graph, and then all of a sudden we have a hole, and then you continue on. We would have a discontinuity at that point right there. So it's not possible for us here to have a hole. A jump also cannot occur. So jump would look like this. We have a graph. Make this a little smaller. Let's see if that works. There we go. Okay, it's working. Okay, so a jump would look like this. We have a graph, and then all of a sudden jumps up. Maybe it's solid here, and then keeps going. Anywhere we have a jump, we have a discontinuity. So it's not possible for us to have a jump either. Now, a vertical asymptote would look like this. Let's say we have our xy axes. Let's say at some x value, we have an asymptote. So the graph comes in like this, and maybe on this side it goes down like that. Well, we can't draw this without picking up our pencil either. Therefore, it wouldn't be continuous at this point. So none of these would be the correct answer because we can't have any of those for it to be continuous everywhere. All right, next thing, let me turn my phone down a little bit here so we don't get interrupted. All right, next thing. Okay, from this graph, state each x value at which f is discontinuous. For each x value, determine whether f is continuous from the right, from the left, or from neither. All right, so let's take a look at this graph here. Let's just imagine we're starting out, we're drawing, and there's no problems, then all of a sudden we have a hole, okay? So we have a hole here at -4. That means we're going to be discontinuous there. We'll come back and talk about left and right in a second. Then I keep going, everything's fine, I have a solid dot. Then I have to make a jump. At that jump, I have a discontinuity, so we're going to have discontinuity at -2. Here I draw, I have a little corner here, which is okay, because I don't have to pick up my pencil to keep drawing. Then I have a hole, then I have another jump. So I'm going to have a discontinuity here at 2. And then I continue to draw, and this looks like it's going to go down forever. It's hard to tell because they don't really include the asymptote, but it looks like there's an asymptote there. In any event, there's a jump in the graph or a break in the graph. So I have a solid dot here, and it continues on, no problems. So I have another discontinuity at 4. So we have 4 places where we are discontinuous: -4, -2, +2, and +4. So let's first talk about -4 and talk about whether it's left continuous or right continuous there. So what we're going to do is, for it to be continuous, what has to happen is as we approach that discontinuity, we need our function to be defined there. So I would need this to be solid as I come in from the left, which it is not. All right, it's an open circle, so it is not continuous from the left. From the right, same thing. I'm approaching some value, but I have an open circle there, so it's not defined. So because there's a hole, I cannot be continuous from the left or the right, so it's neither. Now at -2, if I come in from the left, notice I'm approaching a value, and when I actually get there, I have a nice solid dot there. And because my function is actually defined there as I come in from the left, I would say is left continuous. Notice that if I come in from the right, I'm approaching a value, but there's a hole, so I can't be right continuous. So I'm going to put N here for neither. Here I'm going to put an L for left continuous. And let's move on to 2 over here. As I come in from the left, I'm approaching a value. When I get there is a hole, so it is not left continuous. As I come in from the right, I approach a value, and it is defined there. Therefore, it is right continuous. And then at 4, as I come in from the left, I'm going asymptotically down to -infinity. I'm just going. Whoa. Weird. I'm learning things about this computer every day. It's going down forever, so I'm not approaching any specific value. but so it can't be left continuous. On the right, I'm coming into a value, and I am defined there. And because I'm defined there, I would be right continuous. So I'd be right continuous at 4. All right, that's number 2. Number 3, state the intervals in which g is continuous. So we have a function g here. So again, what I'm going to do is I'm going to just imagine I'm drawing and trying to figure out where I have to pick up my pencil. So look, at -4 I am defined. So -4 is going to be part of my answer here, right? -4 I am defined. I am continuous as I move to the right. When I get here, I have a jump, right? So because I have a jump, I'm discontinuous here. Now, even though my function is defined here, it has a, it's defined, it has a dot here. On this interval right here, I would have to be approaching a value. In other words, I would have to be going to a solid dot here for it to be continuous at -2 from the left. So what I can say is that on that little interval from -4, that didn't come out very good. From -4, including -4, that's why I put a bracket, to -2, parentheses, not including -2, I am continuous. Then I have to jump, and then I start moving this way. Now notice that everything is fine in between these two values, -2 and 2. The question is what's happening at the ends. And because we're not defined here, and because we're not defined here, we are not right continuous, we are not left continuous here, so I cannot include the endpoints. So I'd say from -2 to +2, I am continuous, not including the endpoints. That's why I use the parentheses. Then I start out at 2, and notice that at 2, I am right continuous here, and it continues to go up, and then I have an asymptote at 4. So I have a break in the graph. So my function can never be defined at 4 because of this asymptote. So I would say from 2, including 2, all the way to 4, but not including 4. And then when I get on the other side of 4, my graph is real nice. I can draw it without picking up my pencil, all the way until I get to 6. And here there's an open hole. So I cannot be left continuous here. So I can't include 6. So I'll say from 4, not including 4, to 6, not including 6. And then I look at this last little segment here. Nice and continuous between 6 and 8. On the left side, at the left endpoint, as I come in from the right, I have an open hole, so it's not right continuous. As I come in from the left, over here it is open hole, so I'm not left continuous, so I cannot include the 2 endpoints. So I say from 6, not including 6, to 8, not including 8. And then what we do is we can just put commas between all of these intervals, and I believe what we get is this one right here. All right, next. Sketch the graph of a function f that is continuous except for the stated discontinuity. It's discontinuous but continuous from the right at x equals 5. So let me just take you to the answer. All I need to do is draw a function that's continuous except at 5, but at 5 it's continuous from the right. So as I come in from the left to 5, I should be nice and continuous, but I should not be continuous from the left. So I should put an open hole here. Then I'm going to have a jump. That's where my discontinuity is. And then from the right, I need to be continuous. So as I come in from the right side here, notice I'm approaching the solid dot, which means it's defined there. So what we're saying is that the limit as x approaches 5 from the right, coming in this way, that's what the little plus sign means, of our function must be f of 5. The function's value at 5 is defined to be the same place we're headed to, from the right. So there's your correct answer. All right, suppose f and g are continuous functions that g of 3 equals 2, and then that this limit, all of this stuff is 25. It says find f of 3. Now the key to this problem is the fact that they tell us that f and g are both continuous, and it's implied it's continuous, that they're continuous everywhere. That means that this statement right here, okay, the statement that g of 3 equals 2, because g is continuous, we also know that the limit as x approaches 3 from either side of that function g of x should be equal to 2. So as we approach 3, our g function should be approaching 2, and at 2 it should be defined to be 2. At 3 it should be defined to be 2. We'll need that. Okay, so let's look at this work here. So let me bring that back up here. All right, so f and g are continuous. Take a look at this limit that we're trying to evaluate. First, we're going to use some limit laws. We're going to pass the limit to each of these since there's addition between them. We're going to pull a 3 out of this one, and that gives us this first piece. And then on the other one, because we have a limit of a product, we can do the product of the limits. And now we just look at all these separately. So what is the limit as x approaches 3 of f of x? Well, hold on. What is the limit as x approaches 3 of f of x? Well, all we have to do is replace x with 3, and that gives us f of 3 here. So that's where this comes from. And then limit as x approaches 3 of f of x again is f of 3. That's this. Notice the plus sign here between them. That's that plus sign. And then what is the limit as x approaches 3 of g of x? Well, we just said that that's equal to 2. And that's because of the continuity and the fact that we know that we're defined at 3 to be 2. So that's where that 2 comes from. And all of that needs to be equal to 25 because that's what we're given. So now what we do is we multiply, let's see, excuse me, we multiply 2 times f of 3 plus 3 times f of 3. That's 5 f of 3s. So I put 5 f of 3 equals 25. Then I divide both sides by 5, and I get f of 3 is 5. And that's it. All right, next one. Go to a different color here. For what value of the constant c is the function f continuous everywhere? So what we have here is a quadratic function. They're not telling us what this constant is, but it's a quadratic function to the left of 3, and then it's a cubic function to the right of 3. So without getting into too much detail, what we're trying to do is we're looking at a function that at 3 it splits. It's a totally different thing on the left side of 3 than it is on the right side. So maybe it looks like this. Maybe it's some sort of quadratic. It comes in, and then look at 3, it's not defined here. So we're going to have like some open hole here. And then the other one is a cubic function, which does something. I'm going to just make it up here. I'll do a different color. And what we're trying to do is make it come in here and meet together and then have a solid dot here so that the whole thing is continuous. So what we need to do in order to make these two meet is we need to adjust this value of c to make them come together. See, we could have this situation where we have a parabola comes in, it's not defined, then we have a cubic function that takes off like this, and we have a jump. We're trying to make that gap there come together. So we adjust the value of c. So here's how we're going to do this. Okay, first of all, let's figure out what, if we need it to be continuous at 3, we need to know what the function's value at 3 is. So the function's value at 3 comes from the second part of the piecewise function because of the equal sign underneath that inequality. So all I need to do is plug in 3 for x here. So 3 cubed is 27. Minus c times 3 is 3c. So that's what we know the function's value is at 3. So again, if we're graphing this at 3, we know the function's value there is actually 27 minus 3c. To the right of it is our cubic function, and now what we want to do is try and come in with a parabola and make it join in here like this. So what we're going to be looking at is what is the limit as I come in. I need that limit to head to this. I need to head to that value. So here's the way I'll do it. The limit as x approaches 3, and I want to come in from the left-hand side of the function, must be equal to 27 minus 3c. But as I come in from the left side of 3, right, on this side, I'm on the parabola, which means I need to be looking at this function. And so what I'm saying is limit as x approaches 3 from the right, the function we're going to look at is that top one, cx squared plus 2x. I need that to be equal to 27 minus 3c. So now I'm just going to plug 3 in for x here. And when I do that, I get, let's see, 3 squared is 9, so 9c plus 2 times 3 is 6, must equal 27 minus 3c. And now this is just a linear equation in c, so I'm just going to solve for c. So I'll add 3c to both sides, and we get 12c, and then I'll subtract 6 on both sides here, and we get 21. And then divide through by 12, 21 over 12. Let's see what goes into both of those. 3 goes into both of those. 7/4. So C should be 7/4. So if I put 7/4 here, I put 7/4 here, then I should get those graphs to meet up. Now we will just view the solution quickly. There we go. C is 7/4. All right. Let's go to the next one. Find the values of A and B that make F continuous everywhere. So we have the same sort of issue here. This time it's a piecewise function. It's 3 of them. So let me see if I can do something real quick. Try and bring something else in. Oops. Bring something else in here. Pardon the delay here, but I think this might work out good if I do it this way. So what I'm going to do here is I'm going to insert that picture that I just got. All right, this is a different program I used to write with and gives us a little more room. Okay, so what we have here are 3 functions, and we have something happening actually at 2 and at 3 our function switches. So at 2 and at 3 we have something happening. To the left of 2, I'm this, okay? So it's doing something, and I'm just going to say it's doing that. And then what happens is, because it's not an equal under there, I have a hole when I get to 2. And then we have between 2 and 3, I'm some sort of parabola-looking thing. At 2, because of the equal sign under the inequality, I am defined. So maybe it looks like this. It goes like that and comes in. And then at 3, it's not defined, so I have open circle. And then over here, this is just a line, okay, on the last part, and it is defined at 3. So I have maybe a solid dot and then a line. Now, we can adjust these 3 functions by changing the values of A and B here. By changing A and B, it has the effect of moving or manipulating this parabola up and down, or perhaps even flipping it over to make it go this way instead. And then I can move this line right here up and down. So the question is, how do we choose our A and B so that everything matches up, so that this thing moves down and then somehow comes into this line so it's nice and continuous everywhere. Okay, let's start by looking at what happens at 2. First of all, in order for it to be continuous at 2, we need the limit as x approaches 2 of our function to be equal to f of 2. Well, what is f of 2? Well, to figure out f of 2, we look at where the function is defined at 2, and that's this one because the equal sign there. So what I want to do is I want to plug 2 into this, and that'll be this right side. So I have a times 2 squared, that's 4a, and then I have b times x, which is 2, so minus 2b, and then I have plus 3. So the right side of this, okay, f of 2 is this. Now what I need to figure out is, what's happening here on this left side. Well, again, remember at 2, we're saying that we're defined, the parabola is where we're defined, so we need this left side to come into that point. So I need the limit from the left to be equal to this over here. So I'm going to convert this to limit x approaches 2 from the left. Now what function do we use if we're coming into 2 from the left? Well, that means x is less than 2 because we're to the left of 2, and therefore we're going to be using this. And so what I want to do is make that equal this. Okay, now if we try and plug 2 into this right now, we get 0 over 0. So before I can do that limit, I need to do some algebra. I factor the numerator as a difference of squares. The right side, 4a minus 2b plus 3. And so these cancel. And now just plug in 2, and we get 4. So 4 must equal 4a minus 2b plus 3. And we can subtract 3 from both sides. 1 is equal to 4a minus 2b. So we have our first equation, and it has 2 variables in it, so I can't solve it. But what we're going to do now is we're going to go look at what happens at 3. So what I need for continuity is I need the limit as x approaches 3 of our function to be equal to f of 3. Now, f of 3, we can figure out what our function is at 3 by looking at where it's defined at 3. So here's where it's defined at 3, so I'm going to plug 3 into this. That'll give me the right side over here. So 2 times 3 is 6, so I have 6 minus a plus b. And remember, I'm working the line over here on the right side is where we were defined. So to figure out what limit we're going to use here, we need to realize that we're going to have to come in from the left because the parabola was not defined there. It had the open hole. So we want to come in from that, and we want to match that up, move that down to this point. So I want this limit over here to come in from the left again of the function. And the function we're going to use, because we're coming in from the left, is the parabola one. So it'll be ax squared minus bx plus 3. And now let's just plug in 3 into this and see what we get. So 3 squares 9, so we have 9a. Here we have minus b times 3, so minus 3b. And then plus 3 must equal 6 minus a plus b. Now what I'll do is I'll get all my a's and b's on one side. So let me add an a to both sides here to get 10a. Let me subtract a b. Let me subtract a b to get minus 4b. Let me subtract 3 on both sides to get equals 3. So now I have 2 equations and 2 unknown variables. So this is a system of linear equations. So I'm going to rewrite it. 4a minus 2b must equal 1. The other equation is 10a minus 4b must equal 3. And there's all sorts of different ways to solve this. I'm going to solve it using elimination, not substitution. What I'm going to realize is that I can get these b's over here to cancel if I can make one of them, like if I can make this one up here a 4b, then when I add these rows straight down, the b's will cancel. So to make that a 4b, I multiply the top row by negative 2. That creates a new system of equations, negative 8a plus 4b. Remember that negative 2 has to distribute to all the entire equation, so equals negative 2. The second equation does not change. And now I can add straight down. So if I add down, I get 2a. The b's will cancel. And over here, I get 1, which means a is equal to 1/2. Once I know what a is, I can come back to any of the equations. I could go here or I could go here and just replace a with 1/2. So I think I'll just use this one right here. 1 equals 4 times a, which is 1/2, minus 2b. 1/2 of 4 is 2. Let me subtract 2 from both sides, and then divide both sides by -2. And I get b is a half also. So a must be a half and b must be a half. Let's see if that matches up with what they got. There we go. A is a half, b is a half. Okay, I believe that's it for that assignment. Yes, it is.